Below is the time-independent motion equation with constant acceleration. But how do we get this equation? In the last part, I used the equations we already know, as well as the area under the curve, to start the derivation of how we find this equation. In this part, we're going to continue from where we left off. So we can start by distributing the VOX into the bracket there, and we get this expression here, as well as squaring numerator and denominator of the bracket on the right to get the expression there. And then from here, we can cancel out one of the AX squareds from the top and bottom. And if we do that, it leaves us with this expression here. And now we need to use an algebraic trick to get rid of the AX in the denominator by multiplying both sides by 2AX. We're multiplying it by 2AX because there's a 1/2 in the term on the right there. So if we multiply it by 2, we'll get rid of this 1/2, which makes the equation look nicer in the end. So if we distribute the 2AX to each term in the bracket and multiply it on the left-hand side too, we're left with this equation here. On the right term here, we can cancel out the 2AX from the numerator and denominator. As well, on the left term, we can cancel out just the AX. And then we have to distribute the 2 into the brackets. And we're left with this equation here. And I also want to note that we do also have the 2AX multiplied on the left-hand side there, where the X minus XO is. Our next step is to expand this bracket. So if we write VX minus VOX squared, we can separate them into 2 brackets and then distribute each term and multiply. And we're left with this expression here. So we can plug this back into our original equation. And once we plug it back in, we get this expression here. From this point, we can see that these 2 terms cancel. And we can see these 2 terms add up to negative VOX squared. And then we can move that to the other side, becoming positive. And we get this expression here for the final answer. And we can note that this equation has no time dependence. So this equation is useful when you are given a constant acceleration question without time. So I just wanted to recap. These are the equations we found for motion with constant acceleration. So the first one we have here is x equal x naught plus VOXT plus 1/2 AXT squared. And then there's the second one, which is velocity. And there's one we found today. And this is an extra one here. Note that this one is an equation that is independent of the acceleration. So you can use that when a problem gives you the values without acceleration. But equations 1 through 3 are the most useful for most of the problems you will see.